Alright, how's it going, everybody? We are into chapter 12. So we're going to be taking a little bit of a detour here, looking at something a little different than what we have been looking at with these distributions, with the chi-square, with the normal curves, and finding hypothesis testing and all stuff. We will be coming back to that. But for right now, we're going to be looking at the concept of linear regression and correlation. And section 1 is really just a bit of a review, just to make sure that you guys are comfortable with the concept of a linear equation, so that we're not, kind of caught off guard when we start dealing with linear regression dealing with lines. So a linear equation in two variables is an equation where the highest exponent on the given variables is 1. A linear equation in two variables is an equation with two variables with exponent 1. So this is kind of our standard form for a linear equation, right? So hopefully you've seen these in your algebra classes. So we do need to be able to solve linear equations, but also to be able to graph them and to be able to interpret what they tell us. Those are going to be particularly important for this class. Okay. So first up, let's talk about the slope of a line. So this is the measure of the line's steepness. We denote slope with an m, and that was, there has some historical context there as well why we do that. As the slope increases, the line becomes steeper, and as it decreases, the line becomes flatter. Okay, so if we have a slope that is very large and very positive, right? So if we had, I guess I should mention this. So a line that rises left to right has positive slope, and a line that falls left to right has negative slope. So if we have a slope of like 2, that's going to be positive, so increasing and kind of, a little more flat. Whereas if we had a slope of 20, that is increasing and very steep. Whereas, negative 3, that's going downward, but only slightly, and negative 30 is, significantly decreasing, very steep, but in the negative direction. We can compute the slope by taking change in y over change in x. This is commonly referred to as rise over run. That's probably the expression that you've used to describe it. So we just get change in y over change in x, and that gives us our slope. Then we have the slope-intercept form of a line. This is probably the most commonly used one. So this is y equals mx plus b, and this is where m is the slope and b is the value of the y-intercept. So the y-intercept is just where the line crosses the y-axis. So the y-axis, right, is this line right here. So that is given to us by b, and then m tells us how the line is moving thereafter. So let's look at this example. Graph y equals negative 2x plus 1. So we have here the 1 is the y-intercept. So this corresponds to the point 0, 1 being on the line. So that's going to be right here. Okay, so that point is on the line. And then right here, we have our slope. Okay, so our slope is negative 2, so what that means, that's the same thing as like negative 2 over 1. So that's going to be down 2, right 1. Okay, so we start at this point, we go down 2, right 1, down 2, right 1, down 2, right 1, so you get some points plotted there. Okay. Okay, and we can also backtrack, right, because if we started like here, down 2 over 1 would get us there. Right, so a point right there and a point right there. And then we're just going to connect the dots as best we can. It's not bad. And there we have our line. Okay, so there's a little bit of practice just with these linear equations. We do need to be able to graph them. But now let's go ahead and look at interpretation. So when we talk about slope, we're talking about what we call average rate of change. So this is the rate at which the quantity being discussed in the equation changes. So let's look at this example here. So the cost c of x, where x is the number of miles driven, of renting a car for a day is $48 plus $1.55 per mile. So what is the independent variable and its units? So the independent variable is always the input variable. In this case, that is x. Okay, so x is our input variable here, because that is purely determined by us, right? It's not dependent on anything. We decide how many miles we're going to put on the car, right? How many miles we drive. So that's independent. And then the units on that, of course, that's the number of miles. So the units are in miles. Now the dependent variable is going to be whatever output value we get, one that's dependent on the input. And that is going to be C of x, which is the cost in dollars. Okay, so our dependent variable is C of x, because the cost of renting the car is dependent on how many miles we drive. Right? If you drive more miles, then it's going to cost you more. If you drive fewer miles, it's going to cost you less. And the units on the cost, that's going to be in dollars. Okay. What is the slope of the linear function and its units? So the slope is the rate of change. Okay, so how much is that value changing? Well, if we look here, so the cost of renting a car for a day is $48 plus $1.55 per mile. So the real key here to recognizing slope and rate of change is going to be this phrasing right here, this per mile, because this represents a change in cost per every mile that passes. Right? So the slope is going to be $1.55, right, or just $1.55 if we just do it numerically. And the units on this are dollars per mile. Okay, so as the number of miles increase, how does the cost increase? Right? So for every 1 mile I put on it, I'm going to incur an additional $1.55 in cost. And then the y-intercept, this is what we would like to call the initial value. Okay, so this is our kind of our starting point. So when the number of miles we've driven is 0, what is our initial value? How much are we paying? And that would be $48. Because no matter what, you're going to pay $48 to rent the car for a day, and then you will additionally pay $1.55 per mile. But that initial cost, that's going to be our y-intercept. So our y-intercept is 48. And the units on that are just dollars, because it's just a dollar amount. Okay. So this tells us, right, if we drove 0 miles on the car, right, we would spend $48 plus 0, right, 0 times 155. So then for the linear function, we have the cost, C of x, equals $1.55 times the number of miles we drive, plus the $48 that we're going to spend regardless of how far we drive. Okay. So this gives us the function notation, right, for this linear expression. So again, this gives us the total cost This gives us number of miles times the cost per mile, and then our initial cost. Okay. So we can interpret these linear functions not only in just mathematical and graphical terms, but also in real-world context, and that's how we'll be using them as well. Okay, so that's 12.1. So let's go ahead and look at section 12.2. So talking about scatter plots. So the idea of the scatter plot is that we're going to be able to look at a lot of different data and be able to see it all on one graph. And that's going to allow us to determine if there are any relationships or any trends among the data, because we can visualize it a lot easier if it's in a graphical form. Okay, so a scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis. The response variable is plotted on the vertical axis. Okay. So let's look at this example. So the data shown below are based on a study for drilling rock. So here we have the depth at which the drilling begins and the time that it takes to drill. The researchers want to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which the drilling begins is the explanatory variable, x, and time in minutes to drill 5 feet is the response variable, y. Draw a scatter diagram for this data. So in essence, they're trying to determine if I go deeper and deeper into the rock, does it become harder and take longer for me to drill into it? Okay, so we're going to take this data and we're going to plot it here on our scatter plot. So hopefully you have your notes handy there. But go ahead and start plotting these. You can plot along with me here. So we got 35 and 5.88. So again, the depth down here, so that's going to be the column here. And then we've got the time up here, that's going to be the second column there. Okay, so let me make this bigger. Okay, so that first one, 35 feet deep, gives us a time of 5.88. So that's going to be right about there. Okay, 50 and 5.99, so it's going to be even just a little bit higher than that. Okay, 75 and 6.74, that's going to be right about there. Okay, then we go up to 95, a little more than 6 there. Okay, so hopefully you can kind of get the idea of what's going on here. So let me just fill in the rest of these. Okay, so you can see it does take a little time to fill in these scatter diagrams, especially when you've got more data. Like that. Like that. 175, 7.62. Right about there. Okay, 185. Right about there. 190. Right about there. Okay. There we go. Trim a little bit of that excess off. Okay. And here we have our scatter diagram, or our scatter plot. So when we're looking at whether the data is related or not, and that's what we're going to talk about in the next section, is kind of how to determine this relationship. But there are several different types of relations between two variables. So a relationship is linear when the points on the scatter diagram follow the general pattern of a line. It's nonlinear when the points follow a general pattern, but it's not a line. And then we say that it has no correlation when the points don't show any pattern. So if we had to take a guess on this one, I would say that these look fairly linear, and we will deal with this example some more later on, but if you just kind of imagine a line cutting right through there, I would say that looks like it goes through the data pretty well, right? The data does appear to have kind of that linear relationship. It's not going to be perfect, it never is, but we're just trying to get a general idea of how good the data is to matching that shape. And if we look at the top of the next page, here's what those would tend to look like. So here we have, right, our linear relationship, where all of these kind of tend in a positive linear fashion. We have another linear relationship where they tend linearly in a negative direction. Then we have nonlinear, where there's clearly a relationship here, but it's not a line, right? So that would be something that we need to keep an eye out for. And then no pattern, right? So we're not really able to fit, right? There's not, because if I draw a line, that doesn't, there's a lot of data points out here too, like that doesn't seem to fit it too well, what we're really looking at here. So those are basically the 4 types that we're going to talk about in here. Now, if we have this linear relationship, like I mentioned up here, there's 2 different types. So there's positively associated. Okay, so this is when, as the explanatory variable increases, the response variable also increases. Okay, so low values correspond to each other and high values correspond to each other. Whereas with negatively associated linear relationships, we have high values of one result in low values of the other. Okay, this is also what we call an inverse relationship. All right, so as this variable is really low, this one is really high. This one goes really high, this one becomes really low. Okay, so those are the different types of linear relationships we can have, positively associated and negatively associated. Okay, so when we come back next time, we're going to take a look at section 12.3, look at the regression equation.